Hello, we will now discuss type 1 error, type 2 error, and the power of the test and calculate these by hand. And this can be confusing, some confusing concepts here, but anyway, you can figure it out if you try. And so I want to do an example of that. So type 1 error, what is type 1 error and type 2 error and the power of the test? When this is my little thing that I do. Is whenever I encounter a type 1, type 2 error problem, when I see that's going to be asked about in a problem, I immediately write it out because it's easy to get things mixed up. And so I immediately write out 1 is hot. That is my little thing to help me remember it. 1 is hot. Now, what does that mean? 1 is hot means in type 1 error, the null is true. In type 1 error, the null is true. And it's an error, so I must have rejected it. But I rejected the null hypothesis. Okay. And so type 2 error is the vice versa of that. Type 2 error is when the null is false. The null is false, but I failed to reject it. I failed to reject the null. Okay. And so whenever you do a hypothesis test and you reject the null, you could have done type 1 error. Okay. If in fact the null was true. Okay. And whenever you do a hypothesis test and you fail to reject the null, in other words, you end up with a high p-value, you could have committed type 2 error. And so that's something that can be asked about. And then the other concept is what is known as the power of the test. The power of the test. And it goes with type 2 error. And it is also when the null is false. It is when the null is false. Null is false. And power is the probability I will reject the null. The probability I will reject the null hypothesis. Okay. And so the probability of type 2 error, they have to add up to 1. And we'll talk about that in a minute. So, all right. So once again, what is type 1 error? Type 1 error is when the null hypothesis is true. Null hypothesis is true, but you reject it. Okay, that's what type 1 error is. And type 2 error is when the null hypothesis is false. Null hypothesis is false, but you fail to reject it. We never accept it. We either reject or fail to reject it, as we discussed before. And then power is the probability that you will reject the null hypothesis when it is false. Okay, so let's look at this example here and answer some related problems. So it says Fabio owns a factory that makes a number of yummy products with peaches. Each day, a truckload of peaches arrives. Fabio wants the truckload to have at least 80% high quality peaches, or he will reject the entire truckload. Each day, he takes a random sample of 500 of the peaches and measures the proportion that are high quality. If he has statistically significant evidence that less than 80% of the peaches are high quality at alpha is equal to 0.05, he'll reject the whole truckload. Describe type 1 error, type 2 error, and the power of the test, and also mention the consequences. Okay, so in order to state type 1 error, type 2 error, we have to define a null and an alternative hypothesis. All right, so in this particular setting, our null hypothesis is whatever is in essence claimed in the problem, or the status quo, and that's 80%. We're dealing with the proportion, and so that's 0.8, where P is the proportion of all of the peaches that are high quality. All right, and the alternative is what we suspect might be true, or what's going to call for a change or a difference. And the key thing here, if it's less than 80%, okay, so it's going to be P is less than 0.8. That's what's going to call for a change or a difference. Okay, if it's greater than 80%, we're fine. It's no problem. We're not going to reject the truckload, or if it's equal to 80, but less than is the problem that we are in essence looking for. So there's our null and alternative hypothesis, which another way of wording this in context here, like P is equal to 0.8, what that in essence means is the peaches are good. Okay, the peaches, or in essence, the truckload is good. The peaches are good. Okay. And the alternative, P is less than 0.8. That means the peaches in general, or the truckload, is bad. So the peaches are bad. And so when we describe these things in context, we'll think of it in that way. So type 1 error. So it asks, what is type 1 error? So we immediately say to ourselves, type 1 error is the null is true, but we reject it. In other words, stating what type 1 error is, we would say, well, the null is true. In other words, P is equal to 0.8, but in other words, the peaches are good, but I reject that and say they're not good. So the way you could word that would be type 1 error is when P is equal to 0.8. In other words, the truckload is good, but I say that I go with the alternative, P is less than 0.8, that the truckload is bad. And the result of that would mean I'm rejecting a good truckload. So that's what type 1 error is. And so whenever you're asked about type 1 error or to describe it, is you're going to say, well, the null is true, but I say I reject that and go with the alternative. All right, so what's type 2 error? So type 2 error means that is when the null is false, but I fail to reject it. And so that's what I'm going to say. I'm going to say, well, the null is false. In other words, P really is less than 0.8, but I'm going to not reject the null. I'm going with the null. So the way you would word that in this setting is you would say the null is false. In other words, P really is less than 0.8. In other words, the truckload really is bad, but I say that P is equal to 0.8, that the truckload is good. And the consequences of that, this means I accept a bad truckload, okay? And that's what type 2 error is when you're accepting, in essence, things that are bad. And so what is the power of the test? The power of the test is you're going to reject the null hypothesis when it's false. In other words, it's the probability that when the null is false, I'm going to reject it. And so in this setting, it's the probability when you have bad peaches, probability that when you have bad peaches, you're going to say that they're bad and reject them. And so power is the probability that I will reject a bad truckload when in fact it is bad. Okay, so that is, and this sort of logic is asked about a lot. This calculation we're fixing to do isn't asked about that much, but this sort of logic thing with type 1 and type 2 error is asked about a lot. But like I encourage you to write it out every time like this, and so you won't get your logic mixed up. Okay, so that is type 1, type 2 error in there, and the power of the test and their consequences. All right, what value the sample proportion would cause Fabio to reject the truckload? All right, so the premise of what's going on, so Fabio is doing this test, okay? And the premise of a test, if we assume that P is equal to 0.8, okay, this is what, in other words, if we assume the null hypothesis is true, which in general testing, that's what we do. And so here's what our sampling distribution would look like if the null is true. It's going to be centered at 0.8. In other words, the sampling distribution is every value P hat could possibly take in repeated sampling. Fabio is going to take a sample, and if it is statistically significantly less than 0.8, we're going to reject it, okay? So if the null is true, our P hats are going to be centered around 0.8. And so if we get one of these P hats that's like really close to 0.8, we would say, well, we have no reason to reject it. It's plausible that's differences due to sampling variability. But the alternative is telling us the direction, in essence, that we're going to reject the null. If we get a P hat that is way less than 0.8, we're going to reject it. So in other words, somewhere way down here, if we get a value that's way less than 0.8, we're going to reject it. Well, how far below 0.8 does that have to be? That's what alpha tells us. Alpha is 0.05. So alpha is the area of the curve that we're rejecting. So here is alpha 0.05. Okay, it tells us in essence where the cutoff point is, that anything beyond here, we're going to reject. And that is what we call our rejection region, okay? And then anything up here, we fail to reject. We never accept, we either reject or we fail to reject, okay? How can we find the value of P hat that's there? Inverse norm will tell us. We did this sort of problem in chapter 2. So what we will do is we will say inverse norm, and then the area, my left area is 0.05. The mean of my P hats is 0.8. And then the standard deviation of my P hats, and we did this in chapter 7, we've done it for the last few chapters, it's going to be the square root of 0.8 times 0.2 over, and our sample size in this problem is 500. So our N is equal to 500. Okay, and so this is 500. And once again, that form, so this would be our left area. That is the mean of our p-hats. That is the sigma of our p-hats. And once again, hopefully you know by now, that formula for our standard error is right here for proportions, the square root of p times 1 minus p over n. Okay, not like that. And so anyway, so let's do that. Let's make that calculation there. And so we will say, so you remember, so inverse norm is on the distribution menu right above the vars button. So I go second vars, which is distribution, and go to inverse norm. And our left area is 0.05. Our mean of our p-hats is 0.8, and the standard deviation of our p-hats is the square root of 0.8 times 0.2 divided by 500. Right, like that. And so we're working with left area. So we hit enter, enter, and there it is, 0.77058, let's say. Or so this would be equal to 0.770576, plenty of sig figs. All right, so that is this value. If my p-hat is less than that value, that falls in my rejection region. So if I get like 0.75, that would cause me to reject the null. But if I get in my sample value, if I get 0.78, we would fail to reject the null, and we would say that difference is due plausibly to sampling variability. So there we go. And so that's the answer to number 2. What values of the sample portion would cause you to reject the truckload? And the way you do it is by doing inverse norm with your alpha value. Okay, and so that is that. And so then it says this, unbeknownst to Fabio, a truckload arrives that has 76% of his peaches that are high quality. If he takes a random sample of size 500 and finds the proportion of them that are high quality, find the probability of type 1 error, type 2 error, and the power of the test. So what Fabio does every day, he doesn't know the population value when a truckload comes in. He just sees a bunch of peaches come in. And he takes a random sample of 500 of them. And if he gets a p-hat below that, he rejects the whole truckload. Okay. If he gets a p-hat above that, he does not reject the whole truckload. Okay. So he will never know whether or not he's rejecting a good truckload or not. So he's just going by this rule. All right. So what happens though on this particular day, it says on one day, he has a truckload that has 76% of its peaches. So the distribution that is going along with this bad truckload is centered. It is also very normally because n times p and n times 1 minus p are greater than or equal to 10. Okay, so it's going to look something like that. And it is centered at 0.76, this bad truckload. So more than likely, when he takes a sample size 500 and gets a p-hat out of this bad truckload, he's going to reject it. Like let's say it's he gets 0.62. Okay, well that falls in my rejection region, falls in Fabio's rejection region. Okay, and so most of them, but here's the problem. It sometimes when he takes a sample from this bad truckload, he could get one of these p-hats, like let's say 0.78. That falls in the fail to reject region. And so he failed to reject this bad truckload. And do you know what we call that when we fail to reject a bad truckload? That's what we call type 2 error. So type 2 error is in essence this overlap that is right there. So type 2 error is the overlap of this bad curve into the fail to reject region of the other curve. Okay, that's what it is. And so how do we find the probability of type 2 error? So the probability of type 2 error is going to be, it is the area of the bad curve that falls in the fail to reject region of the other curve. And so how can we find the area of a normal curve? It's normal CDF, just like we've been doing since chapter 2. Normal CDF, and then the lower value right here of my shaded region is 0.770576. The upper value is infinity. The mean of this is now 0.76. And the standard deviation is the square root of 0.76 times 1 minus that, which would be 0.24 over 500. The sample size has to stay the same. This is my lower bound. This is my upper bound. This is the mean of my p-hats. That's the sigma of my p-hats. And so let's see what we get. And so we shall say second distribution, normal CDF from 0.770576 0.0576 to infinity. So we'll just hit like 9 billion or something, that'll work. And then the mean is 0.76. And our standard deviation would be the square root of 0.76 times 0.24 divided by 500, like that. And so that gives us that it's equal to 0.28988. That is how you find the probability of type 2 error. It is the overlap of the bad curve into the fail to reject region of the other curve, okay? Now, let's think about this part of the curve. So when you look at this part of the curve, this part of the bad curve, what do these p-hats cause you to do? Well, if you get one of these p-hats, they are in the rejection region, okay? So in other words, they get you're rejecting this bad curve. You know, you're rejecting the null is not true and you're rejecting it. And so what do we call that? So we reject the null hypothesis when it's false. That's what power is. Power is the area of the bad curve that's in the rejection region of the other curve. And it's just going to be 1 minus. Now you could do normal CDF if you wanted. Okay. So power, to find power, it's going to be normal CDF. And it is going to be the shaded area of the bad curve that's in the rejection region of the other curve. And so that's going to be negative infinity, 2.770576. And then the mean of 0.76 and the standard deviation will stay the same, 0.76 times 0.24 over 500. That is my lower bound. That is my upper bound. That is the mean of my p-hats. That is the sigma of my p-hats. And that, as it turns out, is equal to 0.710112. That is the power. In other words, the probability of rejecting the null hypothesis when it's false. Notice these two things have to add up to 1. And so in other words, the either way to find power in this case is 1 minus the probability of type 2 error. Now, doing this calculation by hand has really actually only occurred once on the AP exam, okay? And so it's unlikely to occur. But what occurs all the time is you have to know the fact that the probability and the type 2 error have to add up to 1. Okay, so the probability of type 2 error plus the power have to equal 1. So you have to know that. All right, and so there's that. Then the other thing it asks us about, what's the probability of type 1 error? Now, that's an easy problem. It is always equal to alpha, which in this case is 0.05. So please don't miss that problem. Okay, whenever it asks what's the probability of type 1 error, you just look and see what the given alpha value is in the problem. Okay, and in this case it's 0.05. Okay, and so, and if you think about that, hopefully that will, you know, the type 1 error. What is type 1 error? Well, type 1 error is when the null is true, but yet you reject it. Well, if the null is true, that takes us back to this first curve, 0.8. Okay, the null is true, 0.8. In other words, the p-hats really are centered at 0.8. All right, so, well, what would cause me to reject this good curve? If I get one of these values way out here and that would be, these p-hats are in the rejection region, okay? Well, what's the probability that that's going to happen? Well, it's 0.05, okay? Because it takes up 5% of the curve. So if the null is true, the probability I'm going to reject it is getting one of these p-hats, which is 0.05. So hopefully that would make sense there. And then the last thing, and this is asked about all the time, is what can you do to increase power and thus lower the probability of type 2 error? All right, so what can you do to, in essence, reduce, in other words, to reduce this overlap, to reduce the probability of type 2 error? Well, to reduce the overlap, one thing you could do is increase the sample size. Like, let's say if we increase this to 1 or 2,000, the result of that, now these two curves would still be centered at 0.76 and 0.8, but if you increase the sample size, you reduce the variability, and it would look something like that. Let's say the sample size we made like 2,000, let's say, okay? And this one would be like that. It makes them higher and skinnier to where there's less overlap, okay? So the probability of type 2 error is this overlap there. It's the type 2 error is the proportion of this bad curve that falls in the rejection region here. Well, by by making it less variable, all right, by increasing the sample size, you're making these normal curves taller and skinnier. So there's less overlap. So in regards to number 4, what could he do? He could increase the sample size. So that's kind of one of the main things. Increase the sample size. All right. The other thing he could do, if you think about it, what's the other way of, in essence, decreasing this overlap? Well, you could move this value to the right. Like if you moved it over here, now there's less overlap. Well, how do you do that? By increasing alpha. Like if you made alpha into like 0.07, that would move this over here, and so there'd be less overlap. And so the other thing you could do to increase your power and to decrease type 2 error is to increase the alpha value. Of course, there's a trade-off there. By increasing alpha, all right, you are decreasing the probability of type 2 error, but you're increasing the probability of type 1 error. In other words, increasing alpha is going to increase the proportion of the time that you reject everything, both good and bad. So if they increased alpha here, he would reject more bad truckloads of peaches, but he would also be rejecting more good truckloads of peaches. So the sample size, but the sample size can take more time and money. So there's a trade-off there. The last thing you could do is you could change your hypotheses. You could just move these curves further from each other, and specifically the null hypothesis value, as opposed to 80% being your standard, you could move it to 90%. And that would make you more likely to reject the 0.76. And so you could, change your hypotheses. There you go. That's it. I appreciate you watching this video. So if you want to practice this, we've got, a couple of opportunities. I've got a little bonus sheet that you can do if you want to, to give this a try. And if you have any questions about that, please let me know. And I hope you have a great day.